one results. So remember that um, the scores for the first exam, they don't have to factor into your grade at all, you know, because the last exam can replace one of the scores. So if you didn't do well on this exam, then just think of it as like, you know, you get a mulligan on it, but you need to just figure out what you were expecting to be on the exam or how you were expecting me to evaluate it or whatever. And if you have questions about that, come talk to me. I'd be happy to talk about it. Um, the scores overall were a little low, you know, not horribly low, but on the low side. So I'd love to talk to anybody who wants to talk about uh, how you prepared for the test and what I think you should, you know, do differently to bump your score up a little bit. There's a lot of time to do that. Like I said, this doesn't have to come into the grade, but if it didn't go well the first time, it's not going to go well any of the other times if you keep preparing the same way, you know? Yep. Okay, so quiz 2, which is our first quiz. Um, so first, what is kinematics? Yep, that's right. So if you said anything about just describing motion, if you said anything about relationships between position, time, velocity, and acceleration, those were things I accepted. But I think the best definition of it is describing motion uh, without the causes of the motion, which are forces, energy, and mass. And I didn't mention this before, but if there are any of these that you think I was, you know, you want me to take a look at again, you think I misscored or whatever, I'd be happy to do that, you know, after class anytime. But let's do it fairly soon. You know, I don't want to, what I don't want to do is at the end of the semester look through a million exams when people are like scraping for points. Look it over, and if you have any questions, come talk to me in the next week or so. Uh, what's a particle? Number 2. Um, so a particle is um, an object that's treated as having no length dimensions. And therefore, um, there are no orientations. Um, and all this stuff is just, you know, it's stuff that I said very clearly and tried to emphasize when I talked about it in class. You know, like this is just kind of the level of uh, detail I think you should have in reading the notes. You know, like I'm trying to teach you how to do these problems, but if you're not reading the notes to this, you know, level of detail, uh, you're not getting what I'm saying about how to do these problems. So, um, what 3 things in 1D? Um, so what 3 things must be chosen to express position as a function of time? Um, you have to choose a time equals 0 instant. You have to choose a location that corresponds to a position equal to 0. And you have to choose a positive direction. Number 4, what 3 things determine the effect of air resistance on an object's motion? So I'll just say determine an air resistance effect. Um, the mass, the surface area, or the shape. I accepted either one of those. Really, it's kind of both of those in a way, but I lumped those into a single thing. And then the last thing was speed. And of those, the thing that affects it the most is the speed because it happens to be squared in the equation for air resistance. Number 5, 2 properties of a vector are the magnitude and the direction. Um, Number 6, name 3 quantities that will be represented as vectors in 2 dimensions. Um, well, uh, position is 1, displacement is 1, velocity, acceleration. We've talked about the parallel part of acceleration and the perpendicular part of acceleration. All of those things are vectors. Really, the only quantity that we've talked about that's not a vector is time. So any 3 of those work. And then the last one, the equations. Uh, like velocity is equal to v sub 0 plus at and so on. What kind of acceleration are those relevant for? Well, I did give credit for free fall, but the real answer is constant acceleration. It holds for any constant acceleration. Free fall is the most uh, important case of constant acceleration. Yes. Um, Anybody have any questions about any of those? Yes. Direction and magnitude. That'd be sad if it was marked right and then I came back there and like, oh, you put what? Oh, yeah. Actually, I'd put it in the other order too, I think. And anyways, any order is fine. Any other questions? Okay. So now let's go through all of the problems in exam 1. So the first one is a position versus time graph, and then it asks you a bunch of questions about it. And the graph looks something like this. For this kind of problem where you have to figure out where the acceleration's positive, negative, where it's speeding up, slowing down, where it's moving in the positive direction, negative direction, I think the way to go is first figure out where things can change. And so you're going to mark off, 2 endpoints. And then the next step is find all the places where the velocity goes from positive to negative. So where you're going from a positive slope to a negative slope. In this case, that's here and here. Okay, so that's the places where the tangent line is horizontal. And then mark off all the places where the acceleration goes from concave up to concave down, the inflection points. Well, the so yeah, mark off all the inflection points, even if it doesn't go from concave up to concave down, I suppose. There's one, maybe there. Some people put one over here. That was fine with me. It doesn't look like it to me, but. And now in each one of these regions, we've marked off every place where the velocity can change signs and the acceleration can change signs. So now just go through and in each one of these regions, figure out what the sign of the velocity is and what the sign of the acceleration is. So in this first region, velocity is positive the whole time and acceleration is positive the whole time because it's concave up. This second region, the slope is positive, so velocity is positive. It's concave down, so acceleration is negative. The third one, velocity is negative, acceleration is negative. The fourth one, velocity is negative, acceleration is positive again, because now it's gone from concave down to concave up. And then the last one, velocity is positive, acceleration is positive. And now you can pretty much just, you have everything right in front of you. You can sort of read the things off. If this is, so. Okay, so this first region, velocity is positive, acceleration is positive. So it's moving in the positive direction because that's related to the velocity. Acceleration is positive, is right there. And it's speeding up. Because the signs of velocity and acceleration are the same. The second one, velocity is positive, so it's moving in the positive direction. Velocity and acceleration have opposite signs, so it's slowing down. The third one, it's moving in the negative direction because velocity is negative. And since velocity and acceleration have the same signs, it's speeding up. The fourth one, it's moving in the negative direction because velocity is negative. The signs of velocity and acceleration are opposite, so that's slowing down. And then the last one, moving in the positive direction, and it's speeding up because the signs are the same. Anybody have any questions about that one? Okay, and then number 2, it says that velocity as a function of time is equal to negative t cubed. And when time is equal to 0, the position is equal to 3 meters. And we want to know first, what's the acceleration as a function of time? Second, what's the position as a function of time? And third, is it speeding up or slowing down? To find the acceleration, we're just going to take the time derivative of the velocity. So the acceleration as a function of time is the time derivative of negative t cubed, and that's negative 3t squared. And you don't need a constant of integration for that because you're differentiating. Part B, for the position, now we have to integrate the velocity function. So this is the integral of negative t cubed dt. And that's equal to negative t to the fourth over 4 plus c. And to find the value of c, you have to use the boundary condition, which says that this function for position is equal to 3 when t is equal to 0. So 3 is equal to negative 0 to the fourth over 4 plus c. So c is equal to 3. And so the final position function is negative t to the fourth over 4 plus 3. Any questions about that? And then for speeding up or slowing down, for this to even have an answer, those need to be like over the whole interval we're talking about. And I didn't specify anything. So over all time, we need to have acceleration and velocity have either the same sign or opposite sign. Changes, then there's no consistent answer. Well, we know that time has to be positive. And so if you look at the velocity and acceleration functions, the velocity is always negative. The acceleration is always negative for all positive times. They have the same sign. For all positive time. And so it's speeding up. Number 3, the algebra can get a little messy. And I wasn't really a stickler for, making everything come out. And I definitely didn't care whether you simplify it at the end. I just wanted to sort of see you think through the idea. Number 3 says a person throws, so a ball is thrown into the air. From an initial height of h, and it hits the ground capital T seconds later. So using these constants in terms of h g, that's 9.81 meters per second squared, and this capital T, we want to find the initial velocity. And then second, what is the ball's height at the highest point? Okay, so here's what's going on. Here's the ground. This ball is thrown up into the air and comes back down. Um, its initial height is h. Um, it hits the ground after an elapsed time t. I'm going to put my 0 position on the ground and my positive direction up. And I'm going to choose my time equals 0. Time equals 0, yes, is going to be when it's released. So the instant it's released. And the time t, I'm going to call capital T, and that's the instant that it hits the ground. Okay, so what do we know? So out of T, A, P sub 0, P, V sub 0, V. We know T, we know A, because it's free fall. We know P sub 0, that's positive H. We know P, because it hits the ground. We don't know either of these, and we're trying to find this. So now we're looking for an equation works, that has V0 in it, and everything else in it is known. And the one that works is this one. And so I'll substitute in the constants that we're given and the values that we know. The position is 0. P0 is H, plus V0 times the time is capital T. The acceleration, it's free fall, so that acceleration is downwards g, so that's negative 1/2 g times t squared. And now we're just solving for v sub 0 in terms of those other ones. So we have 1/2 g capital T squared minus h all divided by t is equal to v sub 0. You can simplify that a little bit. So let's write that as g t squared minus 2h all over 2t. Any questions about that? So the way you always use these constant acceleration equations is you choose one instant that corresponds to the start, the 0 time, and then you choose another instant that corresponds to this t. And since this t is the instant it hits the ground, the position is the position of the ground, which is 0, because I put my 0 position on the ground. It doesn't have to be that way, but you'd end up doing more algebra to get the same thing if you didn't. Any other questions about that one? And then for part B, now we're talking about the highest point. We're calculating stuff at the highest point. So T can't be equal to capital T anymore. Um, capital T is how long it takes to hit the ground. Um, so we'll still keep T equals 0 to be the instant it's released. Our time T is going to be the instant that it reaches the highest point. I'm going to use the same 0 position and the same positive direction. And now that we've chosen a new meaning for T, for lowercase t, we have to go through the variables again and think about what we know. So the possible variables are T, A, T0, P, V0, and V. We don't know T this time. We know A because it's still free fall. We know P sub 0 is still equal to H. We're looking for the height, so this is the one we want. And now we have an expression for V sub 0. Time is equal to 0, we have this. It's an ugly expression, but we know it. So is there a variable that has P in it and everything else in it is known? Oh, I skipped one thing. Also, this is the key. This is what sort of defines for us the highest point is that P has to be equal to 0. Okay, so is there an equation that has P in it and everything else is known? And the one that works is 2A times the quantity P minus P0 is equal to V squared minus V0 squared. And now we can substitute in the things that we know. So 2 times negative G times the quantity P minus H is equal to 0 squared minus, and now we have this hideous thing squared. So G capital T squared minus 2H. And this is all squared divided by 2T squared. I'll write that as 4T squared. Well, now we can divide both sides by 2G, and we get P minus H is equal to, the negatives cancel, and you get G T squared minus 2H all squared divided by 8G T squared. And now solve for P, and you get the quantity G T squared minus 2H squared over 8G T squared plus H. Any questions about that? And then the last one is a relative motion problem. So you have an object inside an elevator that's in free fall. You have the elevator, and you have the ground. And since the object's in free fall, you know that its acceleration relative to the ground is down at 9.81. So the acceleration of the object relative to the ground is equal to negative 9.81 meters per second squared. Okay. Well, let's write out an equation involving acceleration that deals with these three things. So the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the elevator. I'm going to take things off. This is just a 1D problem. Plus the acceleration of the elevator relative to the ground. And you know that equation works because the fraction multiplication works. And so you get negative 9.81 is equal to the acceleration of the object relative to the elevator plus the acceleration of the elevator relative to the ground, given that that's up at 2 meters per second squared, so plus 2. And then just solve for the variable that you want. So the observed acceleration inside the elevator is negative 11.81 meters per second squared. So to someone inside the elevator or a camera inside the elevator, it looks like this has extra acceleration, like gravity's extra strong because of the relative motion. A couple people use different, so I pretty much always look for a way to write it as the object relative to the ground and then deal with the vehicle as the intermediate thing. But there's no reason you have to do that. You can use any form where the fraction multiplication thing works for those variables. So like you could write, for example, the acceleration of the elevator relative to the ground is equal to the acceleration of the elevator relative to the object plus the acceleration of the object relative to the ground. Elevator relative to ground is positive 2. Acceleration of elevator relative to the object is what, I mean, it's not exactly what we're trying to find, but we don't know it. Plus acceleration of the object relative to the ground, that's negative 9.81. So the acceleration of the elevator relative to the object is positive 11.81 meters per second squared. So in other words, if there's a camera fixed on the object, it looks like the walls of the elevator are accelerating upwards at 11.81 meters per second squared. And then the rules of relative motion say the acceleration then of the object relative to the elevator, what we're trying to find, is the negative of this with the subscript switched. So negative 11.81 meters per second squared. So there's a whole bunch of ways that you can do it. I'm not sure how many permutations, but as long as you use the rules right, you'll get the right answer. Any questions about that one? Okay, well, let's stop there and we'll get back into 2D kinematics tomorrow.